This will be the prep video for section 5.2, integration by substitution. I'll demonstrate U substitution here in this video, and we'll kind of get used to thinking about it that way. And then in class, we'll look at it more of a reverse chain rule method, which is faster but does the same thing. But this one's a little bit more straightforward, so we'll start here. So let's think about this. We know how to find integrals for basic functions, right? We know that the integral of x to the n is 1 over n plus 1 x to the n plus 1 plus c, power law. We know that. We know the integral of e to the x dx, just e to the x plus c, exponential. We know the integral of 1 over x dx, which again, we remember that we have this pattern, dx over x. That will be an important pattern to remember, is equal to lim, absolute value of x, plus c. So we know how to do basic functions. So what happens when we get a composite function? What do we do with that? So here's an example. We could multiply it out, right? This would be a polynomial. We could multiply it out, something to the fifth, and keep going it. It will be messy. Is there a way that we can leverage what we know here to handle integrals of composite functions? And the answer is, when was the last time we talked about composite functions? Chain rule. So let's remember chain rule. So chain rule says, and remember this is for derivatives, so chain rule for derivatives said the following: if you start with some outside function with some inside function, a composite function, then the derivative is the derivative of the outside times the derivative of the inside. And then we just put their respective insides in. So this is the derivative. So it seems entirely reasonable that if I started with this pattern and wanted to find an antiderivative, I would be able to do so. So the key for this is going to be identifying this pattern. And in particular, it's going to be identifying the inside function and its derivative. Okay? So let's look at, let me write up the process for that, and then we'll work through a couple of very simple examples. We'll get much more complicated in class. Okay, so let's look at the process. Sorry, I need to erase this right away. Okay, so here's your process. So this is for trying to take a derivative, integral of a composite function. The first thing you need to do is identify the inside and its derivative. That's the first thing. And then the next thing we'll do is we're going to do what's called a U substitution. We're going to set U equal to I, that inside function, and then we know that du will just be that derivative dx. How do we know that? Well, you could think that if you know u equals I of x, then du dx is I prime multiplied both sides by dx. That's kind of an algebraic way to think of it. It's not quite correct in terms of calculus. This you will also recognize as the differential. So that's another way to think about that. So once we have set u and du, then we're going to substitute. Here comes the substitution. And that will give us an integral of the outside function with a u and a du. The whole point then, remember when we started looking at chain rule and trying to find inside and outside functions, the idea was to find an outside function for which we knew the derivative. So that's the same thing here. You want to make sure that this outside function you know the derivative of, because then you just simply do the antiderivative. And once you've gotten the antiderivative, well, excuse me, this would still be a derivative based on this that we're trying to match. Remember, this was our derivative. So we're working backwards. So we have this. We've replaced these parts with u. So now we have that. So that means our answer is just the antiderivative. So e of u And then lastly, substitute your x's back in. So back substitute x. So then you'll finally have your answer. So, okay. And it will end up being E, x is equal to, U is equal to I of x plus C. So this kind of shows you where, if you can find a pattern, you may not need to go through the U part to get to here. And that's what we'll do in class. Okay, so let's look at some examples. Let's start with the one that we led off with. We are looking for the integral of x squared minus 7 to the 5th times 2x dx. So the first thing we ask ourselves is it a basic? This is not a basic function, this is a composite function. So this is perfect for U substitution. So that means the first thing we need to do is identify the inside function and its derivative. Well, I'm thinking this looks like the inside function. Inside function. So that means its derivative is 2x. Okay, so we're going to set this equal to U. So U will equal x squared minus 7. Du will be this 2x dx. Okay, so now we need to go back up here and substitute in pieces. So coming down here, x squared minus 7, that's U. So then U to the 5th. And now look at what we have here. 2x dx. 2x dx, exactly du. What have we turned it into? We have turned this composite difficulty into a very basic function. So we know that this, we can take the derivative, the antiderivative. And that's very simple. We've turned a composite mess into a basic function. Now, finally, we just need to stick the u's back in, the x's back in, because that's where we started the problem. So finally, we would have 1/6 x squared minus 7 to the 6th plus c. So, a problem we did not know how to do became a basic problem, and then just back substitute. We had to have all of this, the 2x dx. You could imagine that we might not have that 2 there. Well, we're going to get to that in class, where we have to mess with the numbers a little bit. It's not hard, but there's a process. We'll go through that. The important part is, while this I might be able to play with, this I cannot. Every variable piece in du has to be here. Constants, I can work with that, but everything else, no. It has to be there. Okay, so let's look at another one. Integral of e to the negative 4x times negative 4 dx. So is it a basic? It kind of looks basic, but it's not an e to the x. So really it's a composite, and that is my inside piece. So my inside piece, let's just go ahead and call it u. My inside piece is negative 4x, right? U is equal to the inside piece. Du is the derivative of this, negative 4, times dx. Okay, so now we need to go back and see if we have all of our pieces. Clearly we have the u, and we have the negative 4 dx. So we're ready to go. So this becomes e to the u du. Trivially easy problem. E to the u plus c. Put the x back in, let's resubstitute for the u back into x's. E to the minus 4x plus c. So the process is very easy. Once you identify the correct inside, find the derivative, basic function. Again, we'll play around with constants a little bit more in class. Okay, so here's one last example. (2x over x squared minus 1 dx). Okay, is it a basic? No. Is it a composite? Yes. I could write it this way, but remember that exponents to the negative 1, that doesn't work with power rule, right? So that means that this looks like it'll probably end up to be a limb. So let's just start. So if we're thinking that it might be a pattern of a limb, we think the derivative of the bottom is in the top. Remember that was our, that's an important du over u is ln u. Okay, so the derivative of the bottom is in the top. Yes, derivative of the bottom is in the top. That means this part right here is our inside. So u is equal to x squared minus 1, our inside. Du is equal to the derivative of this, 2x, dx. And now we need to go substitute pieces. Here we see this 2x dx. So that altogether is du divided by u. X squared minus 1 is u. Again, simple problem. Ln of u plus c. And now we just simply put back in u. So again, the whole process here is once we have identified the inside and outside, and we see that the derivative of the inside is sitting here on the outside. That's the, you'll hear me say that. The derivative of the inside is sitting here on the outside. That means we are matching the chain rule pattern. Once we have matched the chain rule pattern, it's very simple to set up a u substitution just to make it crystal clear. So once I've identified the inside, I set that equal u, find the derivative, plug in my pieces, do my very simple, because by design it will be very simple integral, and then put my x's back in. So that's the process I would like for you to try. All the ones you're going to try, this piece will be complete. All those pieces will be there. In class, we're going to talk about what happens when that is wrong. As I said, the variable component must be there, but the number we can work a little bit with. Okay, that's it.